All right, welcome everybody. First of all, I'd like to thank and acknowledge all of the team members at GSWA that produce great work towards the West Yilgarn project. So we've got a range of geologists from field geologists to geochemists, geochronologists, structural geologists, geophysicists, and metamorphic petrologists, and some great PhD candidates. And this is really the integration of all the data and interpretations that are produced by these experts in their respective fields to bring that all together that really allow us to make robust interpretations for the West Yilgarn project. So the West Yilgarn project, this is the outline here shown by this red line on this map. It comprises all of the geology from the west of the Ida Fault, which runs in through here, all the way down to the Darling Fault, which runs in through there. It comprises the Naria terrain, the UNME terrain, and the Southwest terrain. And it is bounded to the east by the Eastern Goldfield superterrain, and to the north and south by the Proterozoic Capricorn and Albany-Fraser orogens, respectively. Over the years, there's been a series of 100K mapping campaigns, including the one highlighted here in blue that produced 100K, 1 to 100,000 scale surface geology mapping, and all of the orange colors in through here that produced 1 to 100K interpreted bedrock geology maps. So these two series of mapping campaigns covered a large area of the eastern and northern part of the UNME terrain, leaving a big gap also for all the rest of the West Yilgarn project. So in 2020 to 2021, we ran into the COVID year where we ran a special program, which was named then the Accelerated Geoscience Program, during which time we produced a different kind of mapping where we produced this map that we released in 2021, a map for the Southwest Yilgarn that is largely a huge interpretation of all of the existing data set that we had available then, and all being unified using the potential field data, and really integrating all of the geochemistry, the geochronology, the isotopic data sets, and so on, and the metamorphic and the structural history, to produce a new kind of maps, and that we are now trying to grant truth and test with the different methods and for the future. One of the major outcomes of this map was the redefinition of the boundary between the Southwest terrain and the UNME terrain. We are now placing this boundary in here, where it used to be going through here along the UNME shale zone, and then would go northwest all the way through here. Now we're dividing the West Yilgarn gap into three main broad areas, which we will use so these are the Southwest area, the Midwest area, and the Northwest area. I'll just have a few take-home messages for these three areas. As you've probably seen already, we've released the seismic section for the Southwest 1 seismic section, which runs in through here in the southern part of the project area. And we've released that preliminary time-migrated image, and you can download it from our website if you haven't already done so. You'll see that from the new geochronology we get, we'll see that the Southwest terrain is older than we thought it was, or that we published in 2021. We've worked a lot as well on our understanding of the meaning of the corriging tectonic zone, which is this zone that runs in through here just against the terrain boundary, and I will talk a bit more about that during the talk. We are now seeing this as sharing some similarities with younger Proterozoic orogens by the elements of some form of crustal thickening and exhumation processes happening in the late Neo-Archean. For the Midwest region, this is where the other two seismic lines go. There's the Midwest 1 line and the Midwest 2 lines. The acquisition has finished earlier this year, and we are now in the processing phase. We started some form of IBG work in through here as well to complement the existing mapping. And we have some new ideas as well that we want to show and test. And for the northwest section, which is really looking at the narrower terrain and the boundary with the northwestern UNME terrain, we're really in the data acquisition phase at the moment. We've started fieldwork a couple of years ago, and we're collecting a lot of granite geochemistry data and geochronology data to start building a sufficient data set to be able to make a map of the kind of the southwest one. All right, so if we make some sort of a time-space plot for the West Yilgarn project, this will look a little bit like that. I'm using and combining two different kind of figures in through here, one from the compilation that was published in Tim's report earlier last year, 2 years ago now, wow. And I'm using an extract from David Moll's publication as well, who had a time-space plot for the whole Yilgarn, but I'm using just his narrower terrain one. In the green colors in through here, we're looking at the ages and stratigraphy for the greenstone packages. And then in the light pink colors, these will be the magmatic supersuites divided into the darker orangey colors for the granitic suites, and in the dark green colors, the mafic suites. So the history of the UNME terrain can broadly be subdivided into two main age groups, a 3 to 2.9 GA group, which is the coeval deposition of the Southern Cross supergroup, together with the emplacement of granitic magmas of the Thandara supersuite. Then there is a large magmatic hiatus here until we resume deposition of the Murchison supergroup from about 2.82 GA down to 2.7 GA, and coeval with the emplacement of the Anean and Austin Downs supersuites. Then after 2.7 GA, we don't have any record of younger greenstones deposited in the UNME terrain. But if we go to the southwest terrain, this is where we start to see the deposition of the Boddington and Bellingup greenstone sequences. And at that time, we see the emplacement of granitic rocks from 2.7 to about 2.610. And these ages, these granitic suites, are in place both in the southwest terrain as well as in the UNME terrain and into the narrower terrain as well. Of course, the narrower terrain, as you all know, contains a much older history. There is a large time gap here that is not represented here, and a really different scale that is not represented on this figure. But the narrower terrain contains much older rocks, starting with the oldest rocks in Australia at about 3.7 GA with the Mibri Gneiss and Manfred complex, and they go down to about 3.3 GA, and some younger at about 3 GA as well. All right, looking at the large scale, at the lithospheric structure for the West Yilgarn, I'm showing here the latest MOHO map from OSMOHO 2023, and then the gravity in the middle and the neodymium isotopic map on the right. We can see that the northern UNME terrain is dominated by a region with a MOHO about 33 kilometers deep, which is quite different to what we see in the southern part of the project area, where the southern UNME terrain as well as the southwest terrain has a MOHO averaging from about 36 kilometers down to 42 kilometers based on this data. This deep MOHO in the southwest terrain coincides with a large gravity anomaly of the southwest terrain and a relatively juvenile signature in the isotope dataset. Conversely, the gravity high of the narrower terrain and northwesternmost portion of the UNME terrain coincides with a thin crust and a really evolved old basement, as shown by the isotopic dataset. And we've got here the Q isotopic zone, and this really juvenile zone in the north-central portion of the UNME terrain, which coincides broadly with the low gravity area in this area, apart from the localized dense greenstone belts in through here, but overall the background is a relatively low gravity and a really thin moho. So although we may think that between these three data sets there should be some pretty straightforward relationships, in fact it is far from the point, far from the case. The relationship between these three is really hard to easily pinpoint. Of course we can try and solve that by the traditional work we've done so far, but also if we look at other methods, I'm showing here on the top right-hand corner a slice through a P-wave tomography model at 150 kilometers depth from Zhu et al. In PrEP, and which clearly shows that, so this is the Pilbara here, this is the edge of the Yilgarn in through here, we can see the Naria in through there, and we've got the Capricorn orogen that sits in through here somewhere. And so we can clearly see that underneath the Naria terrain and the northwestern tip of the UME terrain, we see a continuous signature with that of the Capricorn orogen, suggesting that the Naria terrain has lost its Archean lithosphere. And this coincides really well with Alan Aiken's figure that he released in paper last year, of this MG number map of the lithospheric mantle, where he has a similar feature in the northwestern part of the project area that shows that a large degrees of mantle refertilization on the margins of the West Yilgarn project area, large degrees of mantle refertilization during what is interpreted to be the result of younger Proterozoic mafic dike intrusions on the margins of the project area. So you can see that in the Naria area, as well as in parts of the southwest terrain, and especially going into the eastern goldfields. All right, so just to finish with my general introduction on the crustal architecture and lithospheric architecture of the project area, I just want to show these two pre-existing lines. So this is the UNME1 line going from the Naria into here, and the UNME2 line going across through there. So this is the UNME line, the UNME1 line here, and UNME2 line here. What we see is a really flat moho, no topography, averaging on the UNME1 line at about 33 kilometers depth, and a little bit deeper on the UNME2 line at about 36 kilometers depth. We see highly reflective mid-crust with really common east-dipping reflectors throughout on both lines. And we see a poorly reflective upper crust, and we see an architecture that is a bit more complex in the areas of the greenstones, and we see the intrusion of post-kinematic granites that show these blank sheets in the seismic data. And then all this is intruded by Proterozoic dikes, which are placed locally along pre-existing shear zones. All right, for the rest of the talk, I will mostly present on the new data that we've got for the southwest Yilgarn, and this is a lot due to the seismic line that we've got printed there at the back. So I want to provide you with enough background so we can interpret this or have a look at this section appropriately. And then I will carry on with a really short update on the Midwest and Northwest areas. So this is the time-space plot that we released at the end of the 2021 AGP program together with this map. And one of the bases for redefining the boundary was that with the available geochronology, the southwest terrain appeared to be much younger than the UME terrain, with no rocks dated so far older than 2.7 GA. Although we knew that there was probably a strong bias in this dataset because we knew that orthogneisses and migmatites exist in the southwest terrain based on existing mapping, but none of these rocks had been dated so far or published anyway. So in the course of this mapping, we identified a region in the southwest terrain that looked older than the rest because it contains distinct northwest striking shear zones that are truncated by the terrain boundary. So we thought that this is an area of pristine Archean architecture that could be a potential candidate for a null portion of the southwest terrain. So we went collecting rocks in through there and did some geochronology, and we were interpreting some of these orangey bits as some plutons placed into a nodal basement. The plutons return a 2.7 GA age, and the older basement returned a 2.84 GA age. So already we can see that this really sharp, clean cut at 2.7 GA is probably not true. We need to add something to our time-space plot. But this is not really news, and we're not really completely surprised about that, because the isotopes were telling us something to that effect already. On the maps, we can see that there are some old basement components that should be present in the southwest terrain. And if we look at this epsilon neodymium plot versus edge, and the epsilon hafnium says the same thing, we just have a bit less data in the southwest terrain, but basically they say the same thing, so we only talk about the one at the top. In the yellow colors, I'm showing the igneous zircons for the southwest terrain. In the blue colors, I'm showing the igneous zircons for the UNME terrain. You can see that all of the model ages return ages older than 2.8 GA, and maybe up to 3.45 and perhaps even up to 3.8 GA. So we knew that the southwest terrain was really coming from something old in the basement. All right, now I'll talk you for the next few slides about our progress in the understanding of the tectonics of the corriging tectonic zone. The corriging tectonic zone, so here we've got the gravity, we've got the mag in through here, and then I've got a simplified interpreted structural interpretation for the whole West Yilgarn project. The corriging tectonic zone is that area highlighted here in gray, which we see really well defined in the magnetics. And so it forms a belt that may be up to 100 kilometers wide that shows a really well-aligned series of northwest striking reflectors. Sorry, I've been seeing too much seismic data lately. Magnetic horizons. And we interpret a series of west-northwest striking shear zones with west vergence. And what we see as well is a bit outside of the corriging tectonic zone, within the southern UNME terrain, we see a series of losangic features in through here that are bounded by shear zones that resemble in style those famous ones from the northern UNME terrain. And we interpret that these probably originated in the same orientation as those in the northern UNME terrain, but have been rotated counterclockwise during subsequent deformation along the terrain boundary and along the corriging tectonic zone. So we see a counterclockwise rotation, some west verging thrusting direction. If we look at a smaller scale within the corriging tectonic zone, I'm highlighting here three areas, A, B, and C, which is shown here. It's the magnetic data for A with its structural interpretation. B is here with its corresponding interp, and same for C. And we're seeing compressional structures in through there and in through here, marked by thrust, west verging thrusts, and in here marked by incline folds and isoclinal folds, southwest verging. And a bit outside of the corriging tectonic zone, we see evidence as well for sinistral strike slip motion. So we're interpreting the overall tectonic regime for the formation of the corriging tectonic zone to have formed in sinistral transpression. This is the sort of idealized cross-sections that I would draw to show you my understanding of the structure of the southwest. So there is an AB cross-section going from here to there, which is shown at the top, and the CD cross-section goes from here to there. And what we're seeing is that on the eastern part, we're looking at a typical Archean architecture, if there is really such thing. But anyway, the point I want to stress is that we are looking here at the exhumed portion of a mid-crest of granite greenstone terrain. Sorry, I forgot to mention all the metamorphic data we have in the previous slide, but all of this region here shows really consistent pressure constraints at between 5 and 6 kilobars. and the peak metamorphic ages in this region indicate 2665 to 2635 MA event for the formation of the corriging tectonic zone and an exhumation of these rocks from 6 kilobars to here, to the surface. And so this is the geometry that we're looking at, with exhumation of the mid-crustal portion of the southern UNME terrain, thrusted over the southwest terrain along the terrain boundary. And then we need the normal fault in through here to allow this exhumation. This is a similar kind of geometry for the section on C and D, meaning that now we regard this dashed line here, which was previously interpreted by Myers et al. As the original metamorphic boundary, going from high-grade rocks at the bottom to lower-grade rocks in the northern UNME terrain. We now regard this boundary, which was later interpreted as the boundary between the UNME terrain and southwest terrain. We now regard this boundary as the northeasternmost envelope of reactivation and exhumation, reactivation of these structures and exhumation of these rocks during the 2665 to 35 MA event. Just want to stress that this interpretation is all done pre-seismic data, pre-seismic image. And so this is the sort of working model, my working hypothesis that I want to test with the seismic line that we've just acquired. All right, so this is it. This was the design for the seismic line. It's been fully funded by the Exploration Incentive Scheme and designed to test the interpretations that we made in that 2021 map. HiSeis has been the successful applicant to acquire the data and process the data. And we've seen the image here printed on the wall, and it's been released just ahead of this event, so everyone gets the chance to see it at the same time. The line starts in the Albany-Fraser and links with an existing line, the AF2 line of the southern Albany-Fraser, then goes across the Jara Cut-Up Fault into the Yilgarn craton in more typical Archean architecture, goes across this UNME shear zone system where we preserve potentially lake and greenstone belt architecture and through here. And then we enter the granulite facies, gneisses, and migmatites that we see all the way to the terrain boundary of the southern UNME terrain. The corriging tectonic zone is interpreted to start from here to there, and we see a series of major structures running across. And then we will image the terrain boundary at this point, and then we enter the southwest terrain. And the southwest terrain from here to the Darling Fault can be broadly divided into three main domains. We've got this first domain in through here that is characterized by these west-northwest striking shear zones that I talked about before. And to the west, they are truncated as well by the series of northwest striking shear zones, which we interpret to have been at least reactivated during the Proterozoic. And then we enter the triangle through here that looks a little bit different. I'll tell you about it in a minute. Then we pass the Darling Fault and image the Perth Basin and then the Proterozoic Lewin Inlier. And then the line ends on the coast at Hamlin Bay. Some relationships to the known mineralization for this line. We run through the Laking Greenstone Belt, this nickel endowed greenstone belt in through here within the UNME shear zone system, and we hope to see the crustal architecture of the greenstone belts in through here. Then we run into a series of major structures, a long strike of Griffin's Find, for example, and then we enter this region of the Catalan Gold region, and also these shoots along a major crustal boundary in through here. We enter the southwest terrain where we go just south of the Red Hill vanadium titanium deposit, and further to the west, eventually we enter into that triangle I just talked about a minute ago. Geologically, it looks a little bit different. We have the Whitley VMS deposits in through here, as well as Greenbush's lithium pegmatites in there. All right, so this is it. You've probably all seen it on the wall already, but let me just run you through it, through what I understand from the map, and see if we see the corresponding features on the seismic section. So I've plotted here all these arrows and text come from my understanding from the map, and we can have a look at whether we see these features on the seismic section or not, and if we see new features in the seismic section that we had not identified during the mapping. So probably first I should start with the location of the new terrain boundary. Sits in through here, and we're pretty happy to see a major structure going all the way down through there, and maybe you can possibly take it all the way up to here. The core region tectonic zone goes from here to about there. Again, we see a major structure running through here, and see a series of east-dipping reflectors, really dense network of east-dipping reflectors, some of which will be interpreted as thrust, another probably will be the migmatite layering that we see as we interpret all this region as exhumed from mid-crustal levels, possibly from around here, exhumed to the surface along over the southwest terrain. We see here in the geophysics a structure that we have not identified during the mapping, which is this one in through there, that runs and soars into the upper crust somewhere, which would potentially as equally be regarded as the eastern edge of the core region tectonic zone, or alternatively as the northeast boundary of exhumation of the high-grade rocks of the southern UNME terrain. Currently, we interpret this boundary to be here with the UNME shear zone, but doesn't look like necessarily the best candidate for it when looking at this section. Now, if we look at the southwest terrain, we see three main sections as I've described from the map. One that I will refer to as a pristine Archean architecture in through here. And then this is the region that has been affected by these northwest striking shear zones of Proterozoic age. And then there is that triangle which contains Whitley VMS deposit and grain bushes, an architecture that is in through here. And then there's the Perth Basin and Lewin layer. If we look at the deep part of the section now, so this is converted into depth. This is a depth section. We see a really well-defined moho on the eastern part of the line at about 40 kilometers depth, which is pretty deep. A complex moho geometry in through here, and then perhaps we can take it going even deeper all the way down, right underneath the terrain boundary. So maybe we can take the southwest terrain to come all the way to here, and perhaps here in some form of a wedge, possibly in some form of a crocodile structure. This will be for us to interpret in the future. And then I'm not sure exactly where we take the moho after that. Maybe we take it somewhere in through here. All right, just really briefly, a quick update on Midwest. Tim will be largely talking about that, so I won't talk much about this. I will just talk about the location of the seismic lines and what we may wish to test with those. So there's the location of the MW2 line and MW1 line. This is the Yilgarn dome here for reference. And this is the dashed line I've mentioned before, the all-terrain boundary. Maybe we should probably take it in through here instead, based on the geophysics that I see here. Anyway, this will be done when we work through making the interpreted bedrock geology map for the region. And based on the geophysics and on here I'm showing also all the dots are all granite geochemistry data. We can potentially interpret some major crustal boundary running in through here. Again, something that we would like to test when the line is processed. All right, and for the northwest, where, as I said, we're really just at the data collection phase at present. I will not show any interpretations. I just want to show you a bit how much extra new data we've got and some new ages that we have for the area. So this was the status of GSWA geochrone shown by the stars and geochem shown by the green dots before we started fieldwork up there. We've added about 375 new granite geochemistry data for the region, which is plotted here. and about, I think, 17 new geochrone results for the Naria. We've mainly worked in that central part of the Naria terrain on the Barrow sheet, and I will not go into any detail of that. Tony will do that much better than I can. And just to show that we've really added a lot of geochemistry data, especially in this central region. But also we started to work on the other side of the proposed boundary to see the difference between the two, and we started to work as well in this region. And just as a summary, I just want to show some summary of our existing geochronology or recent geochronology for it. We've dated Paleo to Mesoarchean magmatic rocks, some of which can be assigned to the Uradan gneiss at 3495-ish. Others can be identified as part of the Dougal gneiss, which contains inheritance of Uradan gneiss. We have here a new series of granite dated at about 3275 MA, which return all a low calcium granite classification. And this 3275 MA, I don't think is well recorded at the moment in the Naria. It forms a relatively wide area in the central part of the Naria, and it contains mostly Uradan gneiss xenocrysts and a little bit of Dougal gneiss xenocryst population at present. We have one that can be assigned to the Milga gneiss as well. And then we enter into a Neo-Archean magmatism, which our new data fit well with the 3 stages of neomagmatism that were proposed by Matt Rowe in his 2022 publication, where he sees the Neo-Archean magmatism to happen in 3 stages, one at around 2.74 GA, one at around 2.675 or 680, and one around 2.63 to 2.64 GA. So this is stage 1, stage 2, and stage 3, and some of them complex, to say the least, some very complex inheritance signatures. All right, I'll just leave you with this slide of conclusions. We've got the Southwest that is older than previously thought. We start to understand a bit better the tectonic regime for the formation of the corrosion tectonic zone, where we look at it as an exude mid-crustal architecture over some form of thickened crust in the late Neo-Archean. We got the release of the seismic section, SW1 seismic section, which confirms the location of the UNME southwestern boundary proposed in 2021 and confirms the proposed tectonic regime for the corrosion tectonic zone. It provides context for known mineralization in the southwest and reveals other major crustal shear zones which may turn prospective. We see a complex full crustal architecture that will inform us on the amalgamation processes that form the Yilgarn craton overall. For the Midwest, the 2 lines, the acquisition is done, and we're going into the processing phase with high size. We started working on IBG, producing an IBG for the region, and we have some ideas that we want to test as well. And for the Northwest, just the data collection phase, and I've just shown you some of the results. Thank you.